All right, hello everyone. Welcome back from all of the great breakout sessions that were going on throughout the day. I hope everyone had a lot of fun in those breakouts, getting to meet with the team that nominated you and some of those researchers, but hopefully also being able to kind of jump around to some of the other research groups and get a sense for all of the great AI research going on at MSR right now across the org. So this is our final session for the AI Breakthroughs event. We're going to wrap things up with a final session of talks, some really interesting technical talks from three researchers here at MSR. And then, so we're going to have three talks kind of similar to what we did yesterday. We'll have all three talks in a row, and then we'll bring all of the speakers together for a panel-style Q&A. But just like yesterday, I encourage you all to type your questions into the chat throughout the talks or after the talks are over, and we will try to answer some in the chat like throughout the talks, but then we'll get to all the rest of them in the Q&A after that. So I'm going to kick things off first of all with our first speaker. So it's my pleasure to introduce Shamsi Iqbal. From the Information and Data Sciences Group at Microsoft Research. Shamsi has done a lot of great work focused on work and on multitasking and attention and ways to support sort of good work practices in the modern work landscape. And so today we're going to hear a talk on micro productivity. So take it away, Shamsi.
Hello everyone, and thank you for joining this session. I am Shamsi Iqbal, a researcher in the Information and Data Sciences Group in Microsoft Research. In this talk, I will be talking about how productivity research is changing as our landscape of work is changing, and how some of our ongoing work fits into this changing new future of work. Please go ahead and add your questions to the Hub channel. After this recording, I'll be here to answer any questions that you might have. So I wanted to start off by acknowledging the amazing team that I had privilege of working with over the past few years. With any great work, in the background, there are tons of people working together, collaborating, and that's how you come up with research that can actually impact a lot of people. So the bottom two rows I want to call out especially because these are our amazing interns who come and work with us every summer and help us produce some of the research that I will be describing today. So I wanted to start off with some motivation behind this work. The traditional way of being productive is setting aside time to focus and get work done. However, the fact of the matter is that user attention is fragmented. And part of this fragmentation comes from the fact that human beings are natural multitaskers. Some of you might be listening to this talk and also maybe answering emails or doing something else on the side, and we are able to do that. We want to and tend to do multiple things at the same time, but often we also overestimate our ability to multitask efficiently. Contrary to what we might believe for ourselves, we face challenges in protecting our attention from both external and internal interruptions, and also in directing attention to the right thing at the right moment. So while we don't want something like this, if we think about it, micro moments exist in many times during the day. Take, for example, you're waiting for a talk to start. You are waiting in line to get coffee or your food. You are waiting for the elevator to show up. So there are these little bits and pieces of moments that if you put them together, it becomes a substantial chunk of time. And I would also like to introduce you to the new normal, which is our current reality. Most people, especially information workers and students, are now currently working from home or attending classes from home. And this presents some unique challenges that productivity researchers did not have to think about before. Now, we are either coexisting with a lot of other people who each have different goals, and they may not share your own goals and your need for productivity at the same time, or their goals are not aligned. There are also other people who are living alone. They're missing the opportunity to work with their collaborators, to be together to brainstorm, and that has a mental tax. And it makes it just more difficult for people to focus on one single thing. They either interrupt themselves or they keep getting interrupted. So they have to switch and back and forth between the tasks they're trying to focus on and other tasks that are demanding their attention. So I wanted to start off with talking about new ways of getting work done. What is ironic is that the research that I'm going to talk about is not necessarily new. We had been looking at this for quite a number of years, but in the current situation, it seems to be quite applicable. So I want to introduce the notion of microtasks. Some of you may already know about these, but basically the idea of microtasks have their root in psychology literature. And the definition that I like to use most is the research of Knudsen and Enquist. Microtasks are essentially perceptual units of behavior. They're chunks of a larger task that combine together to achieve a broader goal. And microproductivity is the transformation of these bigger goals or productivity related tasks into smaller manageable chunks that you can do in a few seconds, few minutes, or something that can be done in a reasonable amount of time. So if you decompose a larger task into its component microtasks, then we can start mapping these microtasks into the various micro moments that exist throughout the day. So now instead of having to set aside a long period of time to do a larger task, you can essentially pick out those smaller microtasks that can be done independently and try to do them, some of them in your micro moments. So that's kind of like the general idea around microproductivity. So I wanted to quickly emphasize, especially in the context of working from home and interleaving, microtasking has some distinct benefits in terms of task switching needs, which we increasingly find happening as we work from home or work in attentionally challenging scenarios. So multitasking is happening when attention is switched between multiple things of interest. What happens with microtasks is because these things are so small that you are also doing rapid task switching. So if a microtask gets interrupted, it's so small that you can actually finish it before you move on to the next thing. So in some sense, microtasks are probably more resilient to the negative effects of multitasking that we all talk about. So let's talk a little bit about microtasking in today's world, because you may already realize that we are already doing some of these. So when we think about microtasking, or we think about, okay, we're on the go, we have a few seconds, what can we do? We check email, we maybe do some communication, we chat, we can check things off our to-do list, or we can do some quick browsing. What we typically don't do is that we don't think about writing an entire paper using micro moments, or creating a presentation using micro moments, and God forbid, coding, absolutely out of question. So essentially, we feel that complex tasks are not compatible with micro moments. So I wanted to quickly highlight two microtasks. So I think that all of us are probably well aware of crowd workers, and they tend to have these smaller things that they can do, and they can do many of them. These are tasks that can be completed without requiring much context. And then there's also automation. So you could imagine that you could identify parts of a task that can be automatically completed. A very naive example is that you could automatically identify a sentence that needs some correction, and the system could correct it for you without having to invoke the user. And then there's also, of course, self-sourcing. You decide that this is a microtask that you need to do. You don't want to do it right now, so you self-source it for yourself. And so you can find a small chunk of time where you can actually go and address that microtask. So in terms of self-sourcing your own task, what can be self-sourced, or what are suitable microtasks? So I would like to emphasize here is that we are not proposing that everything can be microtasks. They can't. But there are some parts of your broader task spectrum that can be actually microtasks. And these are typically that tasks that can be done rapidly without requiring much context. So an example could be is that you're writing a paper, you need to find a citation, but you're also in flow, so you don't want to break that flow and go and to your citation manager and drag it out. But you can do that task later if it is presented to you when you have a few minutes at your hand. And the other things that can be microtasks are tasks that for which information is not immediately available, so that they need to be deferred. And so the next question is that, well, how do we do it? So many of us might be already doing this manually. You could imagine that, well, here's a timeline of a day, and then sometimes you're on your computer, sometimes you have your mobile device. You have to take into account what screen real estate you have available. So if you have a laptop, you can do a bit more. If you only have a mobile device, so you're not only challenged in terms of your available cycles, attentional cycles, but you're also challenged in terms of the space that's available. So the task needs to fit into not only the micro moments, but also the device that you have access to. So for the next few slides, I'm going to do a whirlwind tour of the micro-productivity research that has happened at Microsoft over the past few years. And I have links to most of the papers that we have published, and I'll be happy to answer some of the questions or that you might have at the end of this session. So we started off looking at two main domains. We started off actually looking at writing because we felt that this was a complex enough domain that had a few things that could be microtasks, and we wanted to use that as our example domain. And part of the reason why we picked this is that, again, as I said at the beginning, we don't typically think of writing or content creation as something that can be done in small chunks of time. We usually want to set aside focused time to do these kinds of things. So this is just an overview of kind of like what we wanted to do. We wanted to understand the domain. We wanted to understand how we can create content from scratch. We wanted to see how we can actually edit a content and how can we create workflows. And this also led us into understanding how we could apply the same principles in a different domain. So talking more about generalizability. So we started off with looking at, well, I mean, if we create content from scratch and mostly via microtasks, can we do it? And so we took kind of like Michael Bernstein's Find, Fix, Verify model, and we modified a little bit. And so we broke it into, we want to collect content, we want to organize the content, and then we want to expand the content into writing. And the first two steps, or well, actually in this case, all three steps can be done on your mobile device using micro moments. You generate a bunch of ideas, you then group the ideas into a group of themes, and then for each theme you write one or two sentences. This could be done in a few seconds on your mobile device or on your laptop computer. And then there's a final stage, which is basically integrating all the outcomes, and that is something that you can't do via microtask. That has to be done ideally on a desktop computer with a little more than just micro moments. There was also a similar thread. Can you actually use what to write a paper? And so in this case, it was writing a paper, bringing together a bunch of people who can actually create the content, but the coordination of creating the content was happening through a watch. So if you're the main author and you have a bunch of crowd workers, you create all these instructions for them and they start putting the content. So their task is not microtask, but as the coordinator, as the author, all of your coordination is happening just using micro moments. So I wanted to move on to using microtasks for editing, and this is where you can imagine that you have already content that exists and you want to do some editing tasks. So it's almost that you have done the first part of content creation, and so you have some tasks that you already know that you want to do on your content. And so we created this tool called Playwright, and it basically helps you edit existing content on a mobile device via microtasks. And so what it does is that there's a framework that would analyze your Word document, identify microtasks, upload it to a server, and then you could see these microtasks on your mobile phone in a kind of like a game-like format. And so the idea was that we don't want to make everything feel like work. So these are things that you can do in a few seconds, and they're completed in a mobile app in a game-like fashion. And so I don't know whether you can see this very well, but you can see that you're only seeing a little bit of text, and it's asking a person to correct the spelling or fix the grammatical mistakes or decide whether they want to accept or reject a change and whatnot. So we also wanted to see what happens when you are creating content or editing content via microtasks like this, is that, well, what is the quality of the document? And so we are presenting a paper in a mobile HCI this year that actually looks at that experience, is that, well, when are people so how are people creating these microtasks, and what are typically the type of microtasks that people create when they're writing something so that they can remain in flow? When are they completing these microtasks? And then what is the quality of the document when you get back? And so what we find is that in comparison to a mobile task editing tool like Mobile Word, when you present the content to people via microtask, it's very focused. People are able to, in most cases, they're able to do these tasks very quickly and keep engaged. And the other thing is that in most cases, they don't really need the whole document. And people are picking out microtasks that they can actually do in small micro moments. People did them on buses. People did them during their short breaks before meetings and whatnot. So they are picking tasks that they know that they can do in short time and in short attention spans. We also have another way that we can include microtasks in other environments. So for example, we did an experiment where we included microtasks in as people were browsing Facebook, and we wanted to see how it interplayed with people's need to go and take a break and what happens if they see microtasks. And this was a lightweight way of engaging activities that are backgrounded. We found that people could ignore these microtasks just as they would ignore any other kind of non-Facebook task. But after a while, they felt good about engaging with some of them because it made them feel that they were actually completing tasks without getting super engaged with them. We also did some research looking at how we can incorporate the crowd in our work. And so in this research, we looked at if we present the crowd with a snippet of a text, can they go through each line and quickly provide some kind of ranking on whether this is free of spelling and grammatical errors, or you could provide any other kind of question there. And when the feedback goes back to the author, they see an averaged color-coded text that can kind of like give them a sense of the quality of the text that they had. And this is mostly from a copy editing point of view. And so this is how you can incorporate the crowd so that they can quickly give people feedback without having to know too much about the document itself. We also looked at intelligence support during writing. And so if you want to include NLP, for example, to help out people with writing. And so we wanted to compare this with incorporating the crowd or the author themselves. And what we found is that when NLP revisions are typically small, they were typically improvements. And when you have NLP then crowd, the majority of NLP changes, the crowd leave them unchanged. But what we found is that the authors, they tend to prefer their own edits versus when you give it to an independent evaluator, they tend to prefer more of the NLP plus crowd kind of edit. So there's some benefit in incorporating intelligence support, but authors do have some kind of like bias towards their own writing, obviously. And there's also Design for Intelligence work that we published in CHI 2019. And this is a very interesting piece of work where we looked at early user experience design for intelligent experiences while writing. And traditionally, design includes storyboarding and wireframes, but when you're designing for intelligent experiences, none of those actually work because it depends on the context, the underlying data. And so we had some interesting ideas around how we could totally frame this as a different problem and incorporate ways that we could actually test it without having to have the full model in the background. So because of time, I'm going to quickly go over this. So there was some work that we looked at how we can help people ramp up into writing and ramp down from writing, building context and transition, and help people do multiple microtasks on the same content so that they build the context, and that helps them easily ramp up into writing. We wanted to see how we can help the crowd, help build context for the crowd so that the communication between the crowd member and the author is reduced, but the crowd can get the answers to the questions that they might have ahead of time so that they can actually create the content for the author. And finally, the big question is that how can you create these workflows or create these microtasks? This is work that we did with Harman Kaur in 2017, I believe. And so this was a really nice piece of work where we started off with creating a set of limited vocabulary, and these vocabularies were then used to create plans. And so there were a fixed number of steps, and then depending on the type of the task that the step included, it could be done by the author, it could be done by someone else, or it could be automated. quickly, we had looked at how we can use microtasks for ramping up and ramping down at work. And so you could answer a few questions about your plan for the day and how you want to feel about the day. That helps you easily ramp up to work. And at the end of the day, to help you disengage from work, answer a few questions about your reflection about the day. And we wanted to see how that kind of like impacted people's productivity. And it turns out that having that exercise at the beginning and at the end of the day help people have a more sustained productive day. We used some of these lessons from microtasking that we did microtask writing over the years, and we used that to kind of like inform us on how we could do microtask programming. And so there are a few programming tasks that people could do on a mobile device, and we implemented that experience, and it turned out that people actually appreciated the ability to take their programming tasks or microtasks outside of the programming environment and be able to do a few things on the go. And finally, there's also this notion about, okay, so you are driving a car, which probably we're not doing a lot these days, but are there certain things that we could get done in the car without compromising the car safety? And we found that if you could present tasks in a very low cognitive load inducing kind of way, you could get a few things done, but people also try to build context as you're presenting many of these, so you need to be careful about how you present the task to the people. In conclusion, so the question is that is microproductivity the solution to remote work productivity challenges, where switching back and forth is common, resumption of an interrupted task is challenging because you are often interrupted at the wrong moment. So one solution could be is that, well, try to break your task down more and more so that the microtasks are resilient to interruptions, can help with ramp up and ramp down from work. And even as I was recording this presentation, which is quite a number of slides, I had to pause and stop multiple times because there were interruptions, there were like recording issues. And so breaking it down into those like smaller chunks actually helped me create this presentation. And on that note, I would like to end. If you have questions, please put them in the Hub channel, and also my email is here, and as well as my research page. Thank you very much.
All right. Well, thank you so much, Shamsi, for that great talk. And just as a reminder, we'll be having an interactive Q&A with all the speakers after all three talks. But now I'm going to introduce our next speaker. Our next speaker is Alex Polozov, coming to us from the GRAIL team at Microsoft Research, which stands for Grounded Reasoning and Interactive Learning. And Alex is going to speak to us a little bit about his research in Neuro-Symbolic AI and program synthesis. So take it away, Alex.
Thank you, Sean. Right. Hello, everyone. Welcome to the talk. So as Sean mentioned, I'm a senior researcher at the GRAIL group here at Microsoft Research. And we work on the intersection of machine learning and the programming languages research. Deep learning has given us a wonderful way to understand raw data in image, language, or speech domain, and by now in probably most of the domains out there, and learn distributed representations of these, find patterns in large noisy data sets. However, if a data is structured, like we're working with knowledge bases or graphs, this is trickier. And of course, the hunger for many, many examples of data is still a big challenge in the deep learning world. On the flip side, we know how to describe procedural knowledge for the past few decades already. We've been doing that with programs. Programs are interpretable, they provide an easy way to see if they work, and they can generalize well. However, they're very time-consuming to create and acquire extensive prior knowledge, so limited to high-value tasks and to specialists. Not to mention that they are not applicable to many and all of the settings. So we want to learn to use and create programs leveraging the advances of machine learning, and we want to explore their use to make many of the tasks that work with structure more interpretable, systematic, and generalizable. An intersection of these two is what we're calling Neuro-Symbolic AI. The specific approach with which we approach this is called program synthesis, and some of you may be familiar with program synthesis in its most famous application, perhaps flash fill, the feature in Microsoft Excel that automatically generates programs for data transformation from input-output examples. So in this case, for instance, on the slide, if you want to create a combined name column out of these three columns, you could write an Excel formula, but that requires non-trivial syntax learning. Instead, you could simply provide an example in this row 2, and Excel will autocomplete this to generate a combined name in all the rest of the columns by learning a program, the desired Excel formula for you, behind the scenes. In this case, it will actually require a conditional depending on the presence of a middle name. So you will need to provide one more example in order to learn a complex desired formula. Since the last decade of research, program synthesis, starting from data wrangling in Excel, has been generalized to a whole framework of tasks for input-output example-driven learning, and has been used in tons of different applications for web automation and scraping data from web pages, for automatic refactoring of code in Visual Studio from input-output examples, as well as in academia and other colleagues for automatic visualization program learning, and many others. All of these, or most of these so far, have been examples of symbolic program synthesis learning using tools coming from the programming language literature. In the rest of this talk, what I'm going to show is our exploration in how to use these tools as a basis for enabling neuro-symbolic AI, how to bring these two worlds together, the neural world of distributed representations and the symbolic world of structure and logic and reasoning. They can help each other. On one hand, we can use neural networks to guide the symbolic search for programs, and we can use their power to learn from raw data signals. And on the other hand, we can use programs to impose systematicity and generalization in the computation that the neural network performs, and have their reasoning process be interpretable and executable. I'm going to explore this in 3 different applications here. So in order, we'll go over web process automation, automatically teaching an agent to perform tasks over web pages, talking about conversation over tables, how to ask questions over a database, translate them into SQL programs, and engage in a dialogue over a data source, and ask questions over images and engage in logical structure in visual question answering. So let's see all of these in order. I'll start with web process automation. This is a work that started from our AI residency program. You can see a picture of several of our AI residents from Cambridge here on this slide. This has been a wonderful endeavor starting from the last 3 years. So in web-based automation, what we want to do is teaching an agent to perform a task automatically over web pages, like, for instance, sending NLP-related news every day at a certain time. In order to do that, what we need to do today is to show the task step by step by loading the web page, performing all of the required actions, like typing the search term in the search bar, pressing enter, and then actually following up with emailing. Now, this is a simple example, but instances like this happen in real life all the time. When you interact with forms, you interact with legacy applications, you collect data from various web pages, and hours and hours every day I spent on doing this manually. In practice, the problem is known as robotic process automation. Here you see an example of a recording tool Microsoft called part of the Power App suite, and this is a $1 billion opportunity area. So what we want to do is to learn an example of a task from a single demonstration and then generalize that to equivalent websites doing the same task. Importantly, when you're dealing with web pages, you cannot afford to do exploration or simulators. If your task is to pay your rent every month, you can't quite afford to let your agent explore your bank interface and try different programs until it succeeds. You may not have enough funds to succeed. And you really, really want the actions that the agent performs to be guaranteed to be consistent with the demonstration you perform. You want to be able to explore that logic and verify that it works. Now, in program synthesis, this is a classic problem known as programming by demonstrations, where you start with a web page and the user gives you a demonstration of the actions you want to be performed over that web page. On the flip side, the developer has a domain-specific language, or a DSL, of programs in which we would like the actions to perform. So this can be an extension of CSS plus actions over the web page plus some logic in between. And we'd like the computer to take a demonstration and search this language of programs for one program that is consistent with the demonstration and is the desired one. In this example, it's just click one web page element identified on the right of another web page element. The problem with this view is that how the user actually arrived at that demonstration is hidden from us. We don't know the latent reasoning by which they arrived at a certain action, like clicking. And in fact, there's usually hundreds and thousands of programs in the domain-specific language that are consistent with that click, but arrive at it via different logic. And it's very hard to choose between them. They look very similar to the computer. Now, what if, in addition to the demonstration, we also provide this explanation, a natural language description of why and what is being done by the user? So this is known as semantic parsing in the AI literature. And the classic view of semantic parsing is that you start with natural language description, you generate a program from there, and then if you have some other evidence, for instance, you know what is the output of a program if it is to be evaluated over the web page, you just filter the programs from the parsing model until you find the most probable program that also results in the same demonstration. And in there, you cannot, by definition, guarantee consistency. You have to filter for it. Synthesis can give us this consistency. So the idea that we employ in this work is to flip it and say, let's build a generative model of natural language explanations, and starting with a web page and a demonstration, automatically generate a program that is consistent with it, and then ensure that the programs that we learn are both consistent with demonstration and relevant to the natural language explanation. Mathematically, that means that we'd like to maximize both the probability of consistency and the probability of relevancy. Probability of consistency is a symbolic process. We want to ensure that the program is consistent with a web page and the demonstration over that web page. And the probability of relevancy is a classic generative inference models that we know how to optimize in the semantic parsing view. So the end-to-end view process works like this. You start with a task description, and conditioned on the task description, you'd like the agent to emit a program that you later apply to other web pages in this task. What the user gives us is a pair of an explanation and a demonstration. First, we use program synthesis to generate a set of programs that are consistent with the demonstrations, and then we optimize over that set to learn a pair of models that align the program with the natural language explanation. And then we choose among the consistent programs the one that is most aligned. Thus, you get the benefits of both worlds just based on the fact that you use the symbolic representations as a mean to an agent to realize its logic, rather than just perform these actions out of the box blindly. This has several key benefits. First of all, it strictly outperforms either semantic parsing or program synthesis. On many tasks, it generalizes much better to different web pages over the same task, just from a single explanation and a single demonstration on a single web page. And what's also more interesting, it is competitive with reinforcement learning-based methods, which would actually require exploration and playing with the browser in order to get to the same accuracy over thousands of episodes. And from the way we model the problem, we can get this visualization of how exactly the words in the utterance correspond to the components of the program. So not only we understand the logic by which the agent operates, we understand how the constituents of that logic align with what has been said, and we can show it to the user. Okay, so here's another example where we are going to flip the QA model a little bit. This is an example of conversations over data. So in conversations over data, what we want to do is enable question answering over databases. That in this example, we have an interface of some employees and shops in a hypothetical company, and we'd like to give a person an ability to ask questions over this and explore the stats and analytics. In technical terms, this is known as the cross-domain text-to-SQL mapping. Specifically, what we have is a database over a particular domain, a question, and we'd like to map it to the corresponding SQL program that realizes this question. You could map it to the answer directly, but again, having a SQL program in between gives you interpretability, gives you generalization, and allows you to actually gain more trust with the user who can expect the program. Importantly, you need to be able to generalize to unseen domains, because you don't know on which database your model will be applied, and it's not guaranteed that you will have thousands of programs annotated in that domain, so you need to work well out of the box. This is known as a schema encoding and linking problem, where, for instance, let's look at this example of a question over countries. In order to understand that question and map it to the program on the right, we need to be able to say, okay, life expectancy maps to the life expectancy column, that is easy. The official maps to the is official column, slightly harder, but still easy. Countries maps to the country name column and not to any other column that happens to have the word country in it, because it's a primary key. English maps to the language column, which you may know if you're starting from a pre-trained language model, but you would not know if this is some domain-specific term. And you need to be able to understand the structure of the database in order to generate the join clauses and the linkage in the program correctly. This is known as a schema encoding and a schema linking problem. Schema understanding is generally the hardest for human data scientists as they explore a new data set. So no wonder this is also hard for machines as well. The way we address it is starting with a state-of-the-art model in machine learning, the transformer models, but then noticing the following fact. In a transformer model, which is how you would use in natural language understanding, what you usually do is you have all-to-all pairs matching between the set of inputs, in our case, the inputs of words in the question and columns in the schema. However, it is possible to extend this and introduce additional weights on the edges between different pairs of inputs. This has been used a couple of years past in order to enable relative position embeddings in the transformer model, and we use it in order to enable arbitrary edge feature encoding for the same purposes. So we call this model relation over a transformer, and let me explain this in a couple more details. What relation over a transformer allows us to do is to take arbitrary structure of the problem at hand and introduce it into the model encoding without necessarily biasing the model just to that, just giving it as a signal. So in graph neural network, you would limit yourself only to the schema structure. In a vanilla transformer, you would not have any structure and let the model learn it from scratch, which is usually challenging. And RAD gives you a soft bias combining the best of both worlds. In our specific problem setting, the structure that we are interested in is the database schema, foreign key relations, correspondence, but also the pairing between question words, column words, matches between the names and the content, and many, many other things. After you do this, in pre-training or in fine-tuning, depending on the structure of the task, for us, we stay on top of the leaderboard for all the conversational semantic parsing tasks by now. And more interestingly, this kind of model generalizes much better. There's no gap between the dev setting and the test setting, and there's no need for any target domain knowledge or in-domain adaptation for a particular data. We also used it in several different follow-ups on the same setting. One is you can use the same model for conversational interaction, where instead of asking a single question, you engage in a dialogue, as humans often do, to ask new questions, to clarify previous ones, or to correct mistakes of the model. And you can use the same to learn these corrections of mistakes and translate your feedback that someone might give you about a wrongly emitted program into a diff between the wrongly emitted program and the one that should have been emitted. When applying the same method there, fixes about half of the errors that even our model, however good it is, often makes. Okay, the final part of the talk, I want to touch a little bit about visual question answering, also a residency project. So what we saw in the past two previous ones was a program, a symbolic program, being used as a vehicle to enable question answering tasks, typical AI question answering tasks. In here, we will have similar structure, but it will be embedded in the network continuously. So to find a few words, visual question answering starts with an image and a question and asks a VQA model to answer that question, as shown here on the slide. And that requires us to combine two different problems. The perception problem, understanding what actually is happening in the image and which objects or relations are present there, and the reasoning problem, parsing the question into some logic and executing that logic in order to answer the question. The two together form the foundations of visual question answering, and neither pure logical reasoning nor purely neural perception can accomplish the task alone. The perception is usually noisy and uncertain, and thus you cannot rely on it 100% in order to logically interpret what the question asks you and execute that. So for instance, if your perception model misidentified this husky as a wolf, then even if you interpret the question perfectly, you would not be unable to answer it correctly. Yet the phrasing of the question or the visual context of the image should be able to do that. On the flip side, purely neural reasoning is unsystematic. So, and there have been lots and lots of papers that show evidence of our VQA models not being sufficiently grounded in their reasoning capabilities. This is an example of a recent CVPR paper that shows if you ask the same model two similar questions about the same image, their answers can have nothing to do with each other. What we suggest is to actually incorporate logical reasoning into the neural model as an intermediate block in order to ensure that the reasoning is both systematic and properly takes into account the distributed nature of perception. We start with a logical representation, but we will make it continuous. So the discrete logical representation is a description of a scene as a set of variables corresponding objects and relations between them. And this is an example on the right that shows you how you can describe the whole scene in this entire scene graph as a single formula. This formula can be interpreted as a question, can be interpreted as a statement, and you can perform inference over this formula in order to get either the logical value of it, depending on which values you assign to the variables, or if you relax it continuously, the probabilities of the different statements about the same world. And that is what we do in this paper. What we show is that if you start with a question on VQA, you can map it to an implementation of a formula that can be relaxed as a neural network continuously. And once you have that neural network that continuously implements the logic of the question, you can train end-to-end the perception and reasoning systems using that logical representation as your objective. So how it looks like is this, where first you map the natural language description to a program. In this case, the program is the logical formula. And this is done by semantic parser similar to the kind that I showed previously. On the flip side, you use the visual perception models in order to featureize the image and map it into a set of objects and relations with probabilities associated over them. And then the relaxed continuous interpretation of this formula acts as a second half of your question answering model, where the individual models look at the probabilities of the objects and relations in the image and perform steps of reasoning corresponding to the operations in the formula. Like in this example, that would be first step of filtering objects that correspond to its predicate man, and then filtering and then relating from these objects to the other set of objects based on the left geometric relation. All of this can be trained end-to-end once you have a data set of questions and answers and a certain number of intermediate programs. So to conclude, the joint lessons from these and many other projects that we learned and we want to want the audience is that you can use programs, programmatic representations, logical representations, not just as a symbolic tool in order to accomplish tasks that have traditionally been discrete as symbolic, but also as intermediate representations in neuro-symbolic AI tasks, such as question answering, be it over tables or images or web pages or other kinds of context. Once you do that in the right way, you can improve systematicity and the out-of-domain generalization of your question answering, because programs are compositional, just like language is compositional, and you can take the same program once it's generated and apply to other tasks that are similar in spirit but different in details. Programs can be relaxed into interpretable program-like models, like the question answering models of the VQA task that I showed, and the multimodality of the language and vision and other kinds of data that deep learning has enabled us to work with can be applied to program synthesis here as well. Thank you for listening. I'm happy to answer questions later in the Q&A. That is all.
Great, thank you, Alex. So for our third talk and our final talk of the session, I would like to introduce Robert Sim. Robert is from the KTX group at MSR, which stands for Knowledge Technologies and Intelligent Experiences. He does a lot of great work on privacy-preserving machine learning. And today he's going to talk to us a little bit about privacy preservation in natural language applications. So take it away, Robert.
Hi, my name is Robert Sim. I'm a Principal Applied Science Manager in MSR. My team explores problems in natural language understanding and privacy implications of training models using natural language. So why don't we just jump right in? You've probably seen this cartoon before. It's a kind of simplistic view of what's in fact a relatively large attack surface for natural language models. If we think about data that's transformed into a model and hosted in the cloud or on device, there may be for attackers to probe the model in a gray box fashion or black box fashion in order to either extract training examples or determine membership in the training set. In addition, there could be the possibility that some rogue insider probes the model and has complete access to the model. But we also have risks of legitimate users and internal data scientists accidentally exposing customer content just by probing the model directly during normal usage. So this presents some interesting challenges for us of how we safely train these models and deploy them. The current state of the art for privacy in this space is differential privacy, but both differential privacy and many other mitigations, when we apply them, it usually implies some kind of utility loss. And in addition, the guarantees that are provided by differential privacy focus on the worst case possible guarantees, and these actually may be much more conservative than attackers' actual capabilities. So that leaves us some space where we feel that there's room to maneuver and explore, okay, what sorts of mitigations could we develop and what sorts of analysis can we do to understand the gap between a practical attack and the worst case guarantees provided by differential privacy. There are also some other aspects of differential privacy where there's more work to be done. One is it's generally assumed that the examples that we're protecting are independently distributed, when in fact, especially if we're training language models for some user base, such as an enterprise, their emails and written text may be highly correlated. So how do we account for this correlation in the data? There's actually a wide range of privacy research happening at Microsoft right now. It's actually a very exciting space to be working in. I'm really just going to focus on areas related to natural language generation, model assessment, and mitigations that may not necessarily be purely differentially private. In some cases, we'll leverage concepts from differential privacy, but in other cases, we'll try sort of parallel mitigation methods. So if we're going to train and deploy a model, whether it's with differential privacy or any other mitigation, first we need to understand what the privacy risks are and what its privacy loss is. One approach is to just take the epsilon from a differentially private process and say, okay, the privacy loss or the privacy budget is this much. But there's some challenges with this approach. For starters, this is a worst case estimate, and it could hide some issues with underlying issues of fairness in the data that maybe some users are better protected than others. It also assumes that our implementation is bug-free. If we trained using some parameter epsilon, then we really have to trust that the implementation is correct to conclude that the epsilon is for real, and so that makes this this whole process a little bit difficult to verify. And finally, we don't really have a good way to compare with other non-differentially private mitigations. So we've been taking a more practical attack, thinking about thinking about how real-world attacks work and assessing a model's vulnerability or resilience to those attacks. One really important place to start is by assessing privacy risks in the training data itself. So you could imagine just measuring, say, mutual information between the training content and the user IDs associated with that content. This may give you a measure of the general uniqueness of each record in the system and how, on average, users might be exposed just by releasing the content on its own. In addition, once we've trained a model, we can think about assessing the model's susceptibility to various attacks. So we can look at its propensity for memorization. We could apply very kind of naive script kiddie attacks, the tab attack or beam search attack, where we're just basically exercising the model as if it would normally be exercised and measuring how often training examples are generated. And then finally, we can apply more sophisticated attacks like membership inference and understand what's the likelihood that an attacker could determine that a particular user's data was used in the process. There are other approaches. There's some interesting work on estimating epsilon after the model has been trained, and yeah, that's an area that's interesting to us. We haven't explored it in any great detail yet. And so given an assessment approach, the next question is how can we apply it in and develop new mitigations for privacy? And one area that our intern Fatima Mirshgala explored this summer is how can we build privacy into the optimization machinery of machine learning? So high level, why would we want to even do that? For starters, we may be able to improve the average case privacy. So do better than say we get from differential privacy on average across users. And this may improve questions of fairness, especially for underrepresented groups in the data. It also enables us to directly quantify the privacy utility trade-off, and in fact, we can tune for privacy versus utility more easily. And then finally, we can also tie the privacy loss and the whole machine learning loss to any sensitive attributes in the data. So we could basically aim to regularize away any features that might be linked to sensitive attributes in the training set. And I guess one more thing to mention is that the differentially private training algorithms like DPSGD today are still quite expensive to run. There's quite a bit of effort to improve their efficiency, but they're still quite a bit slower than off-the-shelf machine learning. So if we can squeeze out any performance improvements, that's a huge benefit, especially for very, very large models. So 2 questions. How do we define the network privacy loss, and then how will we assess our model once it's trained? We came up with 2 particular mitigations. The first is kind of a standard machine learning model, that language model, where we take the hidden states as their output and feed them through a discriminator. So this will look a lot like a GAN, if you've seen adversarial networks before. And we use an adversarial setup to train the discriminator to try to recognize which user contributed the input training examples. And in the adversarial setup, the discriminator will be driven to produce a uniform distribution. So we're basically trying to smooth away any identifying features in the hidden states, such that the discriminator struggles to identify the source of the input example. And then the second mitigation that we tried was a declustering method, and this is also a smoothing approach, where we train the language model normally, but we provide, in addition to the main training batch, we provide an auxiliary batch. And these examples may come from the same user or from different users. And with the regularization term that we apply, basically measures the L2 distance between pairwise correspondences in the training and auxiliary batch. And if the 2 users in those 2 batches match, then we try to push the examples further away. So we try to maximize this distance. But if the 2 users are different in the batches, then we try to move the examples closer together. And this has the effect of basically distributing examples through the embedding space in the hidden states more evenly throughout the space, without allowing them to cluster on a particular user. And this, in fact, has a quite nice impact on the privacy results. So when we evaluate the quality of the models that we generated, we applied several metrics. I'm just going to share 2. One is the exposure metric from the Secret Share paper, and this metric injects synthetic canaries into the training data at certain repetitions. So we repeated the number of canaries up to 10 times, and then 10, 20, 30, 40, and 50 times. So each individual canary may be repeated up to 50 times. And then we measured exposure, which is really the measure of how easily the canary can be extracted from the model at inference time. And the blue line here is the differentially private solution. And then our 2 mitigations are these 2 lines down below. So as the number of repetitions of synthetic canaries in the data increases, we notice this increase in exposure and differentially private result that doesn't happen in the using our mitigations. And of course, these 3 approaches do much better than the unmitigated model. Unfortunately, they also do much better than a mixed model. It seems like this experiment just by mixing our 2 mitigations didn't work as well. The other measurement that we took against these models was to compare the utility loss of our solutions for different groups of users. In particular, we looked at kind of the best performing and worst performing users in the model, and you'll see that we have this disproportionate loss of perplexity or increase in perplexity for the worst performing users in the model. And all of these models are trained to roughly the same perplexity. So there's a subgroup in here that's disproportionately impacted. In comparison to the differentially private approach, our mitigations showed much lower perplexity loss. Okay, so that project was looking at questions of how can we provide kind of alternative mitigations to differential privacy. Now I want to think about alternative formulations of privacy while taking advantage of all the mechanisms that differential privacy provides us with. So in the enterprise, if we think about the structure of the enterprise, really the question for us becomes one of protecting confidentiality of information and correspondence versus protecting the privacy of individuals. And I'll explain a little bit what I mean by this. If we think about some organization where we have the CEO Alice and the CFO Bob, and then all of the employees in the organization, but some subset of those employees working on some secret project X that is in fact secret even to the rest of the organization. And suppose we have a goal to train a language model for use in this enterprise. And in particular, this is not a model for like public consumption. It's just for use in this business, right? And so it's perfectly fine to encode business knowledge that's specialized to this business. But at the same time, we want to protect things like the confidential discussions between Alice and Bob and the confidential conversations about Project X. So if we think about this in a conventional privacy sense, normally in a differentially private setup, we would train the model to be invariant to, say, Alice's presence or absence in the data, or Bob's presence or absence, or any employees. But from a confidentiality perspective, we'd rather train the model to be invariant to the absence or presence of conversations that take place between pairs of users. So if they have some confidential or highly sensitive conversation, the model should not really be very different, regardless of whether or not the conversation happened. Likewise, we want to protect the model against the, or to be invariant to the presence or absence of some Project X. Excuse me. And finally, though, we have this other constraint, which is really that within the enterprise, if Alice or Bob or anyone else sends a message to all the employees, that particular piece of information is not necessarily private, doesn't need to be protected. It's public to the organization. And so we want to think about models that account for this fact that some of the information in the enterprise is public. So the approach we took with this, which is really kind of a simplified view of the language modeling task, is to look at n-gram extraction. You can think about this in terms of, say you want to extract some set of frequent phrases from a corpus, or even identify language model vocabulary in a differentially private way. Those are two good examples of where n-gram extraction approaches would work well. The state of the art today is probably differentially private set union, which is developed by our algorithms group. But this approach doesn't really think about who's talking to who. It's just treating individual users as the entities that need to be privatized. So, so the way we've set this up is we take the social network of the organization and we frame the problem as one of an edge labeling task, or an edge label counting task, where first we label all the edges positive or negative, depending on whether or not a particular token or a topic or n-gram was discussed between users A and B. And then we try to identify, okay, what's the set of positive labels that are valid to extract from the graph in a privacy preserving way. And the way we frame this is using edge level privacy rather than node level privacy. So trying to extract n-grams such that we're invariant to the absence or presence of an edge in the graph, as opposed to, in the case of like protecting against Alice leaving the organization, we'd be protecting against many edges leaving the graph. At the same time, we also want to consider the likelihood that when Alice talks to Bob about some topic, it's probable that sometimes she's also discussing the same topic with her neighbors, and Bob is likewise discussing with his neighbors. This is a little bit and maybe subtly different from group privacy, where we assume everyone talks about the topic and we have 100% correlation between all the edges. This is kind of a catastrophic challenge for differential privacy because we have to add noise that's commensurate with the group size, whereas in the correlated case, maybe we don't need to add quite as much noise. I'm not going to go into the details of our solution just for the lack of time, but we're relying on an approach based on pufferfish privacy, and then this concept of the Wasserstein distance, which studies the effect of the total shift in the probability distribution of our output measure, which in our case would be the count of positively labeled edges, as the consequence of flipping an edge on on a particular edge in the graph. Flipping the label on a particular edge in the graph. We have some results that we ran on avocado. It's a relatively small data set, so it's challenging to run differentially private algorithms on it. It only has 393 nodes and about 21,000 edges. Largest neighborhood is reasonably large. It has 1,800 edges adjacent to it. Using just basic edge level privacy, we get about 25,000 n-grams extracted. This is far better than the standard node level privacy, kind of the default approach, which would only yield 91 algorithms. And then in our examination of how correlation could play a role, we were able to extract about 230 n-grams compared to group privacy, which would yield only 40. And this W here is really the parameter that's estimating the amount of correlation or the sensitivity of the algorithm. Okay, so that's about all I have to share on this particular topic. We're still running this particular work up, but there's still some important questions to answer, like how do we scale to very, very large graphs? And then how do we translate this problem, which was kind of an edge labeling problem, into a model training one? Ultimately, we want to build a language model that accounts for these correlations and this edge-based approach to privacy. So just to wrap up, yeah, I just want to underscore, I think this is a really exciting time for privacy research at Microsoft. It's one of our core value propositions to our customers. We take it very, very seriously. And at the same time, we understand that there's a lot of value in using their data to provide them with value, and especially our business customers, you know, there's a lot of business insights they could leverage from their enterprise data. So it's really important to us that we understand what are the privacy risks when we train models, and how can we pass on that understanding and provide our customers with the tools they need so that they can unlock value as well. Lots of interesting open questions in this space. How can we apply federated learning and privacy in that space? How could we take advantage of synthetic data generators, use that to enhance our models without infringing on anyone's privacy? How can we personalize models at scale? And ultimately, how can we just improve the overall privacy utility trade-off? So I'll stop there and we'll take questions. Thank you.
Okay, great. Well, thank you for that talk, Robert. So before we get into the Q&A with the panel of speakers, we're just going to take a quick 5-minute break, give everyone a chance to go get a glass of water, stretch your legs, and then we'll be back here in 5 minutes for some Q&A. And see you back here. Thanks. All right. Well, welcome back, everyone. So now we're going to have the Q&A panel with the speakers. So I'm here with Shamsi, Alex, and Robert. So thank you all for your great talks and for being with us for this Q&A. I'm going to start with Shamsi. And if there were a few questions that kind of came in the chat that I think touched on some similar topics and touched on kind of a question I had, and probably a question that you've gotten many times with this work on microtasks. But I mean, it's interesting. It came up in one of our breakout groups earlier today, the concept of flow and the concept of being in like a state of deep focus and attention. And I'm wondering what your thoughts are on that versus microtasking, and especially kind of the timing of when microtasks are suggested to users. Because it seems like that's a real dichotomy there. Like I probably don't want to be, I'm not in a microtask mood when I'm kind of deeply focused on something, but when I'm feeling more fragmented or I'm on the go, that's a great time to be suggesting me microtasks. So is there any work on kind of getting that timing right, or sort of distinguishing those two states, or how do you think about that?
Yeah, I think that's actually a great question. The way that we think about microtasks is it's a complement to your focused work or when you're in flow. And in some sense, microtasks can actually help you with flow, which might seem a bit counterintuitive, because say you are in flow, but there's something that's bugging you and you know that, well, if I don't address this now, I'm going to lose it. But as soon as you switch to address that task, and that's kind of like you're opening up this black hole of distraction. So one way of thinking about it is that, well, maybe you deferred that as a micro task. And so we have some ways of doing that. And so there are some tools that are being released also in Microsoft Word that will help you kind of defer these thoughts as micro tasks. So you could imagine that, well, I want to be, an example is I'm writing a paper, I'm in flow, and I need to add in a citation. I can just, typically what we do is that we add in an inline note. And so that is essentially a micro task. So that's one way. The other one is that, well, again, it's a complement to your focused work. And so when you have a minute, you have, I mean, you're waiting for a meeting to start as an alternative to playing games. So you could look at some of your micro tasks. Now, there's also the flip side is that you don't want to fill up all your micro moments with just work. And so I think that that's something that we have to be really careful about, is that we want microtasks to be something that helps people feel happy and satisfied and productive, as well as helping them feel that they are not getting overworked or burnt out. It might be a way for you to feel that, well, I need to get this done quickly. It's out of my mind. I'm done. I can now focus on whatever I'm supposed to be focusing on, or I can be present in my other experiences. So that's the way that we hope that microtasks will be used. What happens in practice, that's yet to be seen.
Great, thanks. I had a question for Alex. Alex, so I was really taken by like some of the stuff you were talking about, especially in the first project you were talking about, this whole approach, this kind of generate and filter approach to program synthesis of kind of generating a lot of possible matching programs by observing some behavior, and then using the natural language explanations to kind of filter down to select the correct one. So I have a couple of questions along those lines. First of all, I'm curious, like, do the natural language explanations help modify the program ever, or fill in slots or things like that, or is it more kind of purely selecting from a set of programs? And then I'm also just curious about how that approach might apply to other domains where I've seen like programming by demonstration, especially in robotics, where I'm like demonstrating some robot motions, either just through acting things out with my body or moving the robot. But I'm wondering if there's any work on also doing that where I can explain verbally what I'm doing to help doing that program by demonstration.
Yeah. So regarding the natural language, in this particular work, the natural language is a means to explain the latent logic of the agent, the program, rather than change or modify it. You could use it as a modality for modification or for further interaction and conversation about the task, as we do in, say, database question answering, which I showed later, but we just don't do it in this particular case, but it's possible. It is not that natural to the modality of this particular task, where you want to provide a demonstration and explain the logic, and that is how the intent is communicated, both via the demonstration and the aligned text. Interestingly, you do want the aligned text because it mentions entities that are hidden just from the nature of the program. It mentions things like intermediate states of the program, clicking on something next to another button, where another button was selected by a different logic. So there is no easy way to recover that without just searching over the programs. And the natural language gives you the grounding that helps you to explain how to arrive at it. Regarding the other applications, so the robotics one is actually quite relevant. There is plenty of work generally in the literature about programming by demonstration. There is a big difference between a single demonstration that can be translated into a trace of actions, the sequence, and a program that includes logic, such as conditionals, where you need to do something in one case and something else in another. Any individual demonstration is going to only walk you through one situation, the one that you saw in this case. Similarly with loops, when you need to perform a particular action up to a certain condition, and any individual demonstration is going to only demonstrate an unrolling of this loop, a few individual iterations of it. So generalizing from demonstrations to programs is the key task in these kind of settings. We actually have an ongoing line of work where we try to use it as a means to guide an embodied agent in a virtual environment, where imagine a game-like environment where you have an agent navigating a house and performing household tasks like heating up food or washing dishes or any other line of things. And if you just guide the agent with natural language alone and you let them perform the action step by step, the accuracy is quite low. It is difficult to generalize natural language high-level instructions into sequences of steps that need to generalize from one room to another. But it is possible, potentially, if you assume this more programmatic representation. Now, this is ongoing work, so I don't want to talk too much about this, but the short answer is yes, this kind of approach is applicable to, in principle, most settings when you're trying to perform a complex compositional task that needs to be represented as some kind of program with the logic parts and the actionable parts.
Yeah, because it does seem like it would be very applicable in ways that I haven't seen done so much before, but where I'm still thinking about where, like, I'm trying to teach the robot to pick up some objects in the environment, but maybe I'm trying to teach it two things at once. Like, it's my manufacturing robot, and I'm not only just showing it how to pick up cubes, but I also want to convey that it should pick up all the blue cubes.
Yes.
I want to convey some program that it can follow, not just to pick up this one object, but to then kind of continue applying that to the rest of its domain.
Yeah, and you need to, the challenge is also that you are mixing up the motorics and perception and the reasoning of the task, the program itself. And if the reasoning is somehow decoupled in their underlying representations, that makes the teaching easier.
Yes.
That's the one.
Thank you. Robert, there was a question for you that came into the chat, and it's about interpretability. So the question is from Tom asking about, it seems that the lack of interpretability is a major obstacle to having users sort of trust the privacy of current AI. So we're wondering, how do you view that issue? Are there ways to build trust, even if these models are black boxes, as they usually are? Or do we need to solve interpretability first to really kind of convey any kind of ability to trust that privacy is being respected?
Yeah, thanks, Sean. Yeah, that's a really important question. I think maybe there are a couple parts to it. The first is really thinking about interpretability as a diagnostic tool. How can we take advantage of interpretability so we understand why the model did what it did and what went wrong? So in cases where model produces a bad text completion or recommendation or classification, we kind of have all the features at hand that can tell us, okay, is this a problem in the model, or is this a problem with the even with our training data? So that's really about our ability to trust the models that we ship. The other question of how we can leverage interpretability to build trust in users, I think fundamentally we believe that transparency is super important. Really, the open question has more to do with what the UX should look like, and how do we, under what circumstances do we kind of, reveal what happened behind the curtain that led to a particular response from the model. In scenarios like text completion, that's a little bit tricky because it's not like inline we're going to be able to provide a compelling reason or even interfere with the user's flow to tell them why we're delivering this particular suggestion. Yeah, I think that, there's some really interesting open questions there. I'm not an expert in interpretability itself. I would probably defer to other folks in our organization who could give a more, nuanced answer than I can. But I definitely see it has an important role to play.
Great, thanks. Well, that brings us basically to the end of our session. It's just about 3:30. So I once again want to thank our speakers, Shamsi, Alex, Robert. Thank you so much for being here. Thank you for your great talks.
Thank you, Sean.
Thank you, Sean, and thanks everyone for watching.
Sean, thanks everyone.
Okay, so like I said, that's about 3:30. We're gonna wrap up the event. Daniel, did you want to say a few words in closing?
Sure. Yeah, we just wanted to say thank you so much for joining us. It really is one of the great pleasures of working at MSR that we were able to interact with such talented and motivated researchers, PhD students, postdocs. So thank you for sharing your work with us. Thank you for letting us share our work with you and spending these 2 days. It's been a really great event from my perspective, and we'd also like to say thank you to the people behind the scenes, Sarah, Matt, Ryan, to Jen, for all your work putting this together, for hosting, making sure everything flowed from one point to another, answering all our questions. It's obviously wouldn't have been possible without you, so very grateful for that. And I'll pass back to you, Sean, for the final words.
Yeah, so thanks. I'll just reiterate, this was a great 2 days. I hope you all had a lot of fun, and I hope you got to meet some new people. It's a challenging event to try to transform into being all virtual, but I hope that you got a lot out of it. The talks, the fireside chats, the interactive breakout stuff, the poster sessions. I hope you had a good experience. And I do want to say that you shouldn't view this endpoint as like the end of your last opportunity to speak with anyone here. You should totally feel free and encouraged to keep reaching out to us, keep reaching out to, if there are other researchers that you didn't get a chance to interact with over the last 2 days, you should feel absolutely empowered to still email them and reach out to them, because we're all super excited and would be more than happy to talk to every one of you. So with that, I'll wrap it up here and just say thanks again for coming. Bye, everyone.